So I said we were going to do remove first, but that was a total lie. What I have to do instead is that I have to test out this program. So public static void main. Let's go ahead and do doubly linked list of integer. Right, and now we can go ahead and let's do list is equal to new linked list or doubly linked list. And what we'll do is that we'll first test it the first way, but let's go ahead. Doubly linked list for I 1 through 10 list.add I list.add at index 5 0, and let's go ahead and print this out. Sout list. So we can go ahead and print it out, and this will see. This shows that at least the forward links are working. So let's go ahead and check those backlinks by going and saying, hey, print it in reverse by switching these things around. That should make sense. And yep, that totally works. Okay, so we've tested it. Now let's go ahead and move on to our remove method. Our remove method is just those 5 cases over again. Public remove int index so we need if index is out of bounds, then we're going to throw an exception. If, on the other hand, then we have our 5 cases. If size of the list is equal to 1. Yeah, so 1, not 0. Else, if index equal 0. Else, if index equal size minus 1, not size, because that will be the last item. So here are 5 cases. If out of bounds, if we're removing the very last item that the list contains. If we're removing index 0, the head. If we're removing the tail, otherwise, if we're removing anything else. Size minus, and then e to return equals null, and then return to return. All right, so this one's fairly straightforward. I don't feel like I need to draw it. If size is equal to 0, then what do I have to do? Well, what I'm going to do is set head equals null, tail equals null. Just got to set them both to nulls to make sure to say that those aren't pointing at anything anymore. And to return, right, because the item there is both the head and the tail, so we need to set both to null to account for that. So to return is equal to head.data. It could be tail.data. They're the same node. And that's all we have to do. Let's go ahead and draw that. So let's just grab, whoops, this guy over here, move him over here. Right, this guy is going to be both head and he's going to also be the tail. So by having those labels no longer apply to him, by having no longer keeping track of him, so in other words, just say, hey, that's head, tail's null, head points to null, then this will be garbage collected. So that's all we have to do. So let's go ahead and I'll go ahead and construct now what we need for our remove method. All right, so we want to remove index 0, which is the head. So in order to do that, what we need to do is make this guy the new head. But this isn't sufficient, unlike removing the head in a singly linked list, because we still have this back pointer. So let's go ahead and do this first. To return is equal to head.data to store that data and get it back. And now let's go ahead and switch this from being head to this being head. Head.next, or head is equal to head.next, which will advance head by 1. This will store head.next in head, so head will effectively be this node. Next, head dot. Now we need to remove this pointer over here. Head.previous is equal to null, because the head shouldn't point at anything. And now there's nothing referencing this node, so it will get garbage collected. That's all we have to do for that one. To remove the tail, now it's a very similar situation. Tail, so to return is equal to tail.data, right? And now this guy needs to be the tail. So that's tail is equal to tail.prev. And then, finally, we need to remove this over here, which was the .next pointer. So tail.next is equal to tail, or null rather, because that would, if it was tail.next is equal to tail, that would make it circular, which we don't, or that would loop around itself. It would not make it circular. Okay, so as you can see, really the extremities are not too hard to do. So now let's go ahead and say, hey, what if we want to remove this node at I, right? So what if I want to write the ith node? I'll remove the ith node. So what's going to happen here? Well, we're going to do the same. Again, we're going to set up symmetrically so that we do before is equal to, so let's go node E before is equal to return, or sorry, not to return, is equal to get node I minus 1, or index minus 1, index. And then to return is equal to before.next.data, right? Before's next guy's data. Next step. We need to remove this guy. How do we do that? We need to remove this pointer over here and this pointer over here. Now, if we got this guy, that'd be we'd have more flexibility in how we do that, but what we need to do is that we have to take this pointer and get it pointing to get this pointing to before and this one pointing to this guy. So how do we do that? Well, let's see. If we do before.next is equal to before.next.next, like we did beforehand, before.next, so this arrow will store before.next.next. So that will go over there. And it turns out that that doesn't affect our order at all. So next we need to move this arrow. What is this arrow when being referenced from before? And it's important, before in this state, in the current state that it is now. So that would be before.next.previous equal to before. Okay, and now this item with nothing referencing it will get garbage collected, which will make these guys disappear. And that's what we needed to do. So it's not really all too much. We only needed to move 2 pointers, so there we go. let's go ahead and test it. So let's go ahead and say list.remove index 5. And that does so. List.remove 9. List.remove 0. So it seems to work just fine.